we chose to analyze the Little Brute toolbox from Flambeau. This product is a low-cost plastic toolbox formed through plastic injection molding, as indicated by the various ejector pin markings. The Little Brute toolbox features a fold-down handle, 2 front clasps, 2 back hinges, and an interior shelf insert. No paint or other finishing steps were applied to this product, other than removing excess material left over from the injection molding process.
The sub-assemblies of the product consist of the top lid with 2 attached clasps and a handle, as well as the base with an optional shelf insert. Both the top and bottom sub-assemblies are attached using an integrated hinge.
For the original design, each component was manufactured using injection molding with high-density polyethylene. This process involves the injection of molten plastic into a metal mold. To melt the plastic, pellets of plastic are fed into a barrel which contains a rotating screw. Shear forces provided by the screw, along with heating elements, melt the plastic pellets. Once melted, the plastic is thrust forward into the mold. The plastic solidifies quickly and is then ejected from the mold using a series of ejection pins. This process provides an economic means to produce a bulk quantity of the product.
The first change made to the product was a third hinge. This increases the rigidity of the opening and closing mechanism while adding no additional parts and only limited increases in material costs. Our second improvement was changing from 2 clasps to 1. By making the single clasp larger and stronger, the closing mechanism remained strong, while the number of components was decreased. This decreases the manufacturing costs. Our final improvement consists of added sections to the shelf insert. This allows the user to sort small components such as nuts and bolts without adding complexity to the manufacturing process.
A DFA analysis allows for parameters like complexity, functionality, probability for assembly error, handling and insertion detail, and finally any necessary secondary operations. As for the assembly, the new design requires less time to put together, for the hinges do not require any additional attachment beyond fitting the lid onto the box, and only requires the attachment of 1 clasp. Since the manufacturing process for all the components is injection molding, no standardizations were made. As seen, the design complexity was decreased for the redesign due to the decrease in parts, providing affirmation to the improved design of the toolbox. Next, looking at the function analysis, it remained at 80%, for while the number of parts decreased, the practical number of parts decreased the same magnitude, for the only theoretical part for both designs was the shelf insert. From there, the error proofing remained the same within the analysis. However, with only 1 clasp instead of 2, the likelihood for failure of proper orientation is decreased. As for the insertion, with fewer parts in the new design, there are fewer components that require force and/or are difficult to align. Finally, similar to the insertion analysis, the handling analysis was decreased from 2.5 to 2. This was a result of reducing the number of clasps to only 1, reducing the components in need of secondary operation.
The functional prototype of the new design was scaled down and developed using a 3D printer. However, injection molding will still be used for mass production. All components are manufactured using the same injection molding process, because this method is economical for large-scale manufacturing. The decrease in the number of parts in the new design will decrease the overall manufacturing and assembly costs. Additionally, geometry of the new components accounted for the limits and capability of injection molding. All parts are designed to be easily ejected from the mold once solidified.